Alright, so up until this point we have thought of integrals basically geometrically, right? So this integral of this linear function would be the area underneath the graph of the line, in this case from 1 to 2. And we mostly think of it like geometrically like this, right? With the understanding that this integral is also an opposite operation to the derivative. Okay, and we of course know how to solve this. I would anti-differentiate, so I get negative x squared plus 5x, because I did reverse power rule here. And then I'd evaluate from 1 to 2, so I do. Okay, so you know at this point in your integral career how to solve that, right? And you know that this means that the area under the curve here is 2. Right? So this is what's called a definite integral. So it refers to a specific area on a graph. We are going to begin now to work with what are called indefinite integrals. So indefinite integrals are more about the relationship between the derivative and the integral rather than about this geometric interpretation. So in problems where we want to know what function did I take a derivative of to get this result, we use an indefinite integral. The process is pretty much the same. Okay, so we're going to come back to this example in a second, and I'll show you kind of an indefinite version of this problem. But first I want to pause. I want to look at two different derivatives. Okay, we're going to take the derivative of these two functions here. First of all though, think about what you notice about f and g. So you should notice that they're the same except for this last term, this constant term, or the y-intercept term. Okay. So I've picked these functions to be almost the same but a little bit different for a reason. When we take these derivatives, this is now baby food to you at this point in your calculus career, we should notice that they're the same. Right. So f and g, even though they're different functions, give the same derivative. And that's because the derivative of any constant is 0, right? So it doesn't matter if it's 5 or 23 or a million or negative a million at the end, it's still going to give the same derivative. Now, when we take an antiderivative, an indefinite integral, we need to represent that, right? So if I take an indefinite integral of what I just got, this could represent either f or g, right? If this just means take the antiderivative, I don't know which is which. Oh, I forgot my exponent in both of these, didn't I? 12x to the third, 12x to the third. You were probably screaming at your computer trying to get me to fix that. So regardless though, if I took this integral now, I wouldn't know what I would get. There's no way for me to figure out whether this integral came from g or f. So that's why we call this an indefinite integral, because it's missing information, right? It can represent the derivative of many functions. Okay, so the way we do this, easy enough. We're going to take the integral, or rather take the antiderivative, I should say, which would mean I divide, well, let's say I add 1 to the exponent, right? So I know that my antiderivative is going to be x to the fourth. And if I were taking the derivative, I would multiply by 4, but I'm doing the opposite, so I'm going to divide that 12 by 4, right? So I get 3x to the fourth, and then we know this term is going to be an x squared term, and I'm going to divide by 2, so I get 5x squared. And notice I got what I had in f and g, but I have to represent that there could be another number here that I can't figure out based on the information that I have. So in other words, I have to represent that this integral could give both f and g, and I don't know. So an indefinite integral, when I don't have any bounds here, and I just want to know what function this might be a derivative of, I'm going to say plus a constant, plus c. So that's how I represent this indefinite integral. So my constant c could be 23, and that would give me g. Or c could be 5, and that would give me f. But I don't know if I'm just given this integral. Okay. A little bit later in this unit, we're going to introduce a way to solve for c if we have a little bit more information. But for now, when you solve an indefinite integral, you're going to write your result plus c, and c stands for constant. So some number without a variable that would have disappeared when we took a derivative. Okay. So as I said earlier, this example was a definite integral. An indefinite integral would look like this. So it would have no boundaries, no limits of integration. We just say negative 2x plus 5 dx. Okay, so it no longer represents the specific piece of the graph because it has no upper and lower bound. It does represent some function though, although we don't know what exactly that function is. Because my indefinite integral, my result would be negative x squared plus 5x plus c. And I have to leave it at that. That's all the information I have. Okay, so anytime you see no bounds, I'm going to write this so you include it in your notes. So anytime you see no limits of integration, so nothing here, it gets a plus c to represent that constant.